Now, it's not always going to be the case that we are integrating on the x-axis. So now that I'm thinking of the area between two different curves, I'm using that word curve in a very deliberate way. Not every curve is a function, at least maybe not a function of x. So in previous math classes, we would have talked about functions of x have to pass the vertical line test. But here in this picture, I have two different curves and both of them fail the vertical line test. Neither the red nor the blue curves are functions of x. Now, we still might be interested in that area sitting between the two curves. And as it happens, both of these curves can be represented as functions of y. So you could think of a horizontal line test telling us that each of the curves meets a horizontal line in only one place. And for that reason, I can write them as x equals a function of y. So here in pink or red, however that looks on your monitor, we've got x equals f of y. And in blue, we've got x equals g of y. I want to find this amount of area between the two different y coordinates, y equals c and y equals d. All of this is the same stuff as I was talking about for the previous videos. The only technical thing that I need to be careful about now is that the function on top. I don't like the word on top for this picture. Let me go back to the idea of the bigger function. So if I'm asking for which function is bigger and y is the function of, excuse me, I'm even saying this backwards myself. If I'm asking for which function is bigger and x is the function of y, right? X equals f of y, x equals g of y. I'm looking for the bigger x coordinate, which will be the x coordinate to the right. So which of these curves is to the right? It's the f of y. That's the function which is larger. So my area formula is going to be the integral from c to d of f of y minus g of y, all dy. Goodness, that was abstract. Let's actually do an example. So let's take as two different functions, parabola y equals x minus 1, excuse me, line y equals x minus 1, it'll be a pretty deficient parabola, and parabola y squared equals 2x plus 6. So this is a parabola, but it's not a function of x. Let's take a picture here. So in pink, I've got my line, and in blue, I've got my parabola. And I can see in the picture, well, I don't pass the vertical line test, so these will not be functions of x, at least not that parabola piece. That's not a problem, though. I can still set up the integral, writing these out as functions of y, functions of y. So instead of top and bottom, let's talk about left and right. The left function will be x equals 1/2 y squared minus 3. The right function will be y plus 1. These came out of algebraic manipulations of the curve from the previous slide. Just subtract and divide by 2. The integral is going to be between the values of y equals -2 and y equals +4. Again, we got those because those are the two different places the graphs cross each other. So my integral looks like the integral from -2 to 4 of quantity y plus 1 minus quantity 1/2 y squared minus 3. All of that taken dy. And at this point, that's just an integral. The variable might not be a variable I'm used to integrating against. I would suggest you get used to it because the rules are all the same. I just have a polynomial, so all I'm looking for is my antiderivative. Here, my antiderivative is minus 1/2 y cubed divided by 3 plus y squared divided by 2 plus 4 times y. I have to evaluate at both my endpoints and subtract, and I find that there are 18 units of area between the parabola and the line.